We've talked about one-dimensional motion before, but now let's see how the derivative figures in and can allow us to talk about it a little more efficiently. So rectilinear motion, which is one-dimensional motion along a straight line, revisited. And just to bring us back up to date here, let's go ahead and recall some of the notation we used. We let t stand for time. We let s, which was the function s of t, be the position function. Notation, that's what we used. And then we said when t1 was less than t2, so you have two different times, we call the difference in the s values at t2 and t1, we call that the displacement. The displacement of the particle or the object over the time interval, which would go from t1 to t2. So that's some of the language we used before, and we'll get to the other language as we go. Position function graphs can be visualized in a couple of different ways, and they're both handy, so it's good to note both of them. First of all, since s is a function of t, we can graph it in the usual manner. So here's an example. Suppose we have a function like this. It goes up something like this, and then maybe comes down like this. So down here it's at -3. This is 3. This is the s-axis. This is the t-axis. And suppose this maximum here seems to be occurring at 4. This place where it starts going nearly flat is at 7. And then the height of that place where it's going flat would be -1, and the height of this maximum would be at 3. Notice that the function f, or s in this case, is increasing over the region from 0 here to 4, and that it is decreasing otherwise for the rest of the part of the graph that you can see from 4 to infinity. So that's s increasing and s decreasing. So these are all things that we can note from a graph like this, and this is very usual. Now there's another way that people like to graph pictures that involve position function. What you can do is you can imagine that the position function is on a horizontal line like this. You have s here on this line, and then you mark on here the different positions from -3 all the way over to 3. And I'll mark 0 here in the middle, and I believe -1 figured in here. And that was the vertical axis back here. Now we're just writing this horizontally. And then what we do is we say we draw a line which is a curve that represents the progress or the path of the position of the particle. So we start here at -3, and this happens at t equals 0. And then the particle moves, because it's increasing distance, it moves in the rightward direction, increasing distance, until it gets to 3. Then it turns back until it gets to -1. And the point where it turned was time t equals 4. And that happened right here in this time axis. You can see that when t is 4, the function stops increasing and starts decreasing. Increasing means go to the right. In this picture, decreasing means go to the left. So it's increasing, goes to the right, and then it goes to the left, and then it ends here, and at t greater than or equal to 7, it seems to be here at -1 and stays at that particular s value forever. So it never goes any higher or lower. It seems to be staying there. So here is another sort of picture, and you can see that going to the right again is increasing. Going to the left represents decreasing function. So this tells you what the path might be. Now, of course, naturally this would all be happening on the x-axis, but you can't see what's happening if you go this way and then come back. That's why people draw it like this, so you can see that you're going this way until time t equals 4, and then you're coming backwards until 7 and beyond. So both of these graphs will be used as we proceed to examine rectilinear motion with derivatives. Let's look at velocity, speed, and acceleration using the derivative. Definition. First of all, let's remind ourselves, and we had this definition before, previously we called this instantaneous velocity to distinguish it from average velocity. But from now on, we will just use the word velocity for short. And the symbol we'll use v of t for the function. Now that, of course, is the first derivative of the position function. Also helpful to write that as ds dt sometimes. And in the velocity, when you take the derivative, you might have a plus or minus sign. That's essential here. The plus or minus sign in this kind of one-dimensional situation gives direction to this quantity here, which is velocity, but which is a vector. And if you study more calculus or you study physics, you'll be talking about vectors, and vectors have as their basic property that they have a size, a magnitude, and they have a direction associated with them. Direction is indicated here by plus or minus because there are only two directions in a one-dimensional situation. So there's your velocity. Secondly, we will define what speed is. Now, speed and velocity are not the same thing. Velocity is this function here. Speed is the absolute value of velocity. So you just take the absolute value of the first derivative of the position function. Now, speed has no direction because the plus or minus sign, or the minus sign in particular, is wiped out by the absolute value. So it has no direction indicated. You cannot tell from its value. So this is an example of what's called a scalar. It's something like a quantity that is a number that has no direction associated with it. And you'll be studying scalars and vectors if you take any physics or if you go on in calculus. So I have instantaneous velocity, or just velocity. We talked about position before, and now we can go ahead and define acceleration. And again, previously we might have referred to this as instantaneous acceleration. From now on, we'll just call it acceleration. And the acceleration will be denoted by a little a of t, a for acceleration. That is the first derivative of the velocity, also written dv dt. But of course, since the velocity is the first derivative of the position function, we can also write the acceleration as the second derivative of the position function, or the second derivative using the d notation, which of course is d dt of ds dt. That's what this notation means. So the acceleration is really a second derivative with respect to the position function and a first derivative with respect to velocity. Thus, here's what we have as a kind of nice schematic to recognize an organization here between the position, the velocity, and the acceleration functions. You can get from position to velocity by differentiating, taking the derivative. You can get from velocity to acceleration by differentiating or taking the derivative. Later, we'll learn how to go backwards. We'll learn how to reverse. How do you get from acceleration given to you back to the velocity which generated it, or from the velocity back to the position function which generated it? We will do that when we engage the second half of calculus. Let's do an example. Suppose we have a position function, say s of t equals t cubed minus 6t squared. And if you're interested in the units, let's say s is in meters and t, which is time, in seconds. Here's what we want to do. Find the velocity, speed, and acceleration, and so find all of these functions and graph them all. So I'll say graph all four functions. What four functions do I mean? I mean the position function which is given, the velocity, speed, and acceleration that you find. So that's what we're going to do here. Well, finding the velocity, the speed, and the acceleration are easy. It's just a matter of taking a derivative, or in this case, for speed, an absolute value. So we can write those down easily. Velocity is s prime of t. So there's the original s of t. We can take its derivative. We get 3t squared minus 12t. And as usual, we factor. We have 3t, t minus 4. There's my velocity. And my speed, of course, is just the absolute value of this, and we will get to that later. The acceleration is the first derivative of the velocity function. And I think I'll use this form because it's easier. So that's 6t minus 12, which factors into 6 times t minus 2. So now I have both my velocity, my acceleration, and the absolute value of velocity will be speed. So I have all four functions. What you can do here is one of two things to see the relationships between them. You can graph them separately, which is what I will do here, or you can graph them simultaneously on the very same set of axes. And if I were you, I would go ahead and do this on my graphing device to do them simultaneously and see how they relate to each other. But I think the graphing separately will be the way to go here. So let's see if I can do this effectively. I will have 4 graphs, and I want them to be comparable. So I'm going to have to make them look identical as I work my way down the page here. Each one will have the same dimensions and the same numbers on each of the axes. So we'll go from minus 40 to 40 on each one of these, although we're measuring different things in each case. And that's worth keeping in mind, that the position function is measured in a certain unit, the velocity function, the speed, and the acceleration are measured in other units. But these numbers will work as far as just putting the mathematical functions down. And the time will go in units of 2, and we'll go 2, 4, 6, and 8 seconds. And keep these lined up vertically as much as possible. That way we'll be able to see how these relate. And that's always helpful to keep in mind how they relate. Very important if you're studying physics. So the original function here is s of t, which is t squared times t minus 6. I factored it. It was actually t cubed minus 6t squared, but I factored it for the sake of our drawing here. The velocity, you may recall, is 3t times t minus 4. The acceleration, which is the derivative of the velocity, was 6 times t minus 2. And of course, the speed function is the absolute value of the velocity, which is the absolute value of 3t t minus 4. So we have the 4 functions. Let's see what the pictures actually look like. The first one is a cubic function, the position function. And if you graph it, it's going to look something like this. It has what seems to be a local minimum here at 4, passes through 6 here, and of course passes up here through 0. You notice that it's decreasing on the left and increasing on the right, and it seems to have a point here where it changes from decreasing to increasing, and as I said, that's a local minimum. Now, if it's decreasing, that means its derivative is negative. And if it's increasing, that means its derivative is positive. And here would be a place where its derivative would be 0. Well, its derivative is exactly the velocity function. So this function, when it's graphed, should reflect that. The graph of this looks something like that. And notice that when it has a horizontal tangent here, when the velocity or the derivative here should be 0, it is 0. And when on this side, because the function is decreasing, the derivative ought to be negative, it is negative. Look here, it's graphed below the x-axis. And it's positive on this side where the original function is increasing. So this picture reflects this picture, although this one is a graph of the velocity function. So the velocity function is negative, I'll just put an N there for negative, and positive on this side. Now, when we look at the absolute value to get the speed, the only thing that will change, because the right-hand side is already positive, is this negative side will flip up and look something like this. So the graph of the speed function, now it's positive here and positive here, looks like this. The speed function's always positive. Finally, what does the acceleration look like? Well, if we look at this function here, the velocity, it seems to have a point somewhere over here, maybe at 2 exactly, where it has a horizontal tangent. Well, that would be a place where its derivative is 0. Its derivative is the acceleration. So when we graph the acceleration function, we get a picture like this, and lo and behold, its derivative, the acceleration function, is 0 at 2. So all of these reflect one another. And we can see that where the velocity function is decreasing, its derivative should be negative, and so it is. It's negative here. And where the velocity function is increasing to the right, this function here ought to be positive, and it is. It's above the x-axis. So what we have here is, by differentiation, we can get from the position to the velocity and from the velocity to the acceleration. And the relationship is clear in the pictures, that one reflects the other, and they each tell you something about the original function, which is usually all that we're interested in. Now let me give you one more pair of definitions before we continue onward. When we say in common language, speeding up, what that translates into, of course that means increasing speed. What that translates into in terms of our terminology, velocity, acceleration, and so on, increasing speed will happen when the velocity and the acceleration, both of which have plus or minus signs, when they have the same plus or minus sign. That is to say, when the velocity and the acceleration are acting in the same direction, that's when the velocity is accelerating or speeding up. Slowing down, on the other hand, which would indicate a decreasing speed in common language, is going to be when, as you might expect, when the velocity and the acceleration have different signs, or rather have opposite signs. There's only two different kinds of signs, have opposite plus or minus signs. So the velocity is going in one direction, but it's accelerating in the other direction, whatever is opposite to the direction of the velocity. So they have opposite signs. That's going to cause the velocity to decrease, which means for the particle or the object to slow down. So speeding up means the velocity and acceleration have the same plus or minus sign. Slowing down means they have different plus or minus signs, opposites. And we'll use these coming up. Let's use what we've learned to analyze a position function, a position function's graph. And we'll do this by example. Suppose we're given the following position function. S of t equals 2t cubed minus 21t squared plus 60t plus 3. What we want to do is analyze, as closely as we can, the motion of the particle. This is how these problems are phrased. The motion of the particle for some time interval, and we'll just take all times greater than or equal to 0. Now, these problems are often stated this way. They'll give you a function and say, analyze the motion of the particle. That means examine the velocity, the acceleration, the position, of course, the speed, if you like, and how these interrelate with one another. So you can tell where it's slowing down or where it's speeding up. So in this solution, immediately we're going to get the velocity, because we'll need that. The velocity is the derivative of the position function, so let's just go through and take that derivative. 6t squared minus 42t plus 60, with a little algebra, which I will leave to you. If you can factor this into 6 times t minus 2, t minus 5. And that means the velocity function is 0 for t equal 2 and 5. So 2 and 5 seconds, if you like. Then the acceleration is the derivative of the velocity. So let's go through and do that. That would be 12t minus 42. And I'll factor the 12 out because I want to make this as nice as possible. So 12 times t minus 7 over 2. That means this is 0 for t equals 7 over 2. And if this is beginning to look a little familiar, the same thing we used to do when we were examining graphs of functions in general using the derivative, then you're exactly right. That's what we're doing here. All we're going to do is interpret this using the language of rectilinear motion. So v of t, which of course is the first derivative of the position function, that was 6 times t minus 2 times t minus 5. Then the acceleration function, which was the second derivative of the position function, that's 12 times t minus 7 over 2. And then we'll build a chart as we've been doing before. This is the t-axis. This is 0. And since that's 0, in this situation, nothing is happening to the left. Time starts at 0 and continues onward. Then the numbers that were of interest here that came up on the previous page were 2, 7/2, and 5. And then for the first derivative here, it was 2 and 5 that mattered. So let me mark for 2 and 5. For the second derivative, or the acceleration, it was only 7/2 that mattered. And then when we look at the velocity and the acceleration together to talk about speeding up and slowing down, then all of these numbers will matter. and so we will have all these divisions in this final strip, which we haven't had before. So up here in this first strip, what is the velocity? Between 0 and 2, if I put, say, a number like 1 in, here I get negative times a negative. That's going to be positive, so the velocity here is positive. Now, rather than write down some of the things we wrote before when we were analyzing the graphs, let's use the language here. Velocity greater than 0 means that this particle is moving right. That is a plus sign for the first derivative. That says the original function s is increasing, of course. That means that the distance is increasing. Between 2 and 5, we can choose an easy number 2, like 3. That would make this positive and negative, so the velocity here is negative. That means the particle moves left, which is negative for negative velocity. That means the distance is now decreasing. We increased as we moved away, and then we decreased as we moved back. Finally, for numbers bigger than 5, this first derivative is very positive. So this is going to move right again, and that's positive, and so s is going to increase again. And between moving right and moving left, the object has to stop, and so there is a stopping point here. That's where the first derivative is 0. So in this language, we'll call that a stopping point. Now, we might have referred to that as a local max or a local min in previous cases, but here we're just talking about it as a stopping point. Down here, let's look at the acceleration. Between 0 and 7/2, pick a number like 1. Coming over here, that's going to make that negative. So the acceleration is negative in here. And then above 7/2, the acceleration will be positive always. And then between the two, let's see, velocity increasing, acceleration decreasing. They are not going in the same direction, so this must be slows down. Here in this piece, the velocity is decreasing, the velocity is negative, the acceleration is negative, so that means this is speeds up because they are going in the same direction. All that matters is that they're in the same direction. Here, they are again in different directions, so this is slows down. And then finally here, once again, they're both positive this time. They're in the same direction, so that speeds up. Now, this will be easier for you when you have this on the same page as the picture I'm going to draw on my next page. But keep in mind that we have slows down between 0 and 2, then it speeds up between 2 and 7/2, then it slows down again, then it speeds up again. And it only stops at 2 and at 5. It doesn't stop at 7/2. If we draw a position type graph, where this is the position line, where the position here is 0, so I'll even write position here. Remember that the function had a 3 added to the end, so the actual initial position is 3. Then at time t equals 0, we start here at 3. What happens? We continue to move until we reach time equal 2. That was where we had increasing distances. And if you actually work out the distance function, you can see that the distance at time t equal 2, you got up to 55 from 3. Now t equal 2, and this whole period in here, this was slowing down, as we saw from the previous page. Then we turn, when we have a stop, we start moving to the left. We continue speeding up now, so it speeds up to this point. So let me write it down as speeds up. And then continues in the same direction, doesn't change, but now it slows down. And it slows down until you get to time t equal 5, where there is a stop, just like there was a stop back here. So this is a slowdown. But it's going backwards, and the backwards place corresponds to a distance of 28. So here again, before we finish this off, we started at t equals 0, time t equals 0. We slowed down, moving to the right, but slowing down when we got to time t equal 2. Then we started speeding up as we went in the other direction, but then we slowed down again and stopped. And now we will speed up forever in the rightward direction, and that's what the original picture on the other page reveals. So here is a position picture where we go to the right, then we go to the left, then we go to the right, and we go slowing down, then we speed up, then we slow down, then we speed up forever. So these two pictures together, and I'll bring the other one back just to compare, We didn't actually draw a picture here, but you see the slow down, the speed up, the slow down, and the speed up. This is the sort of picture that people will use in these problems, so get used to drawing these. They really are very handy. Time to do an exercise. We'll just do one this time. Here's one for you. I'll give you a position function, and that position function will be s of t equals t over t squared plus 5. And this will be for t greater than or equal 0 time. The time will be in seconds, and the distance of the position will be measured in feet. So that's given information. Here's what you want to do. First of all, part A, find the velocity and acceleration functions. Part B, answer the question, at what time or times is the particle stopped? Good physics question. Next question is, when, at what times or regions of time or intervals of time is it speeding up? And when is it slowing down? And finally, this is not one we did before, but we'll see if you can decide how to tackle this. Find the distance traveled by the particle from the initial time t equals 0 to some time further on, let's just say t equal 5 seconds. So here is your position function. You want to find the velocity and acceleration functions. You want to find what times the particle has stopped. When is it speeding up? When is it slowing down? And find the distance traveled by the particle from the initial time to 5 seconds later. Here's our position function, t over t squared plus 5. And we're taking it for t greater than or equal to 0. That is its domain. And the first question was to find the velocity and the acceleration functions. Well, the velocity we can just get by finding this derivative. So let's do that. It's a quotient rule problem. So t squared plus 5 squared on the bottom, t squared plus 5 on the top, times the derivative of t, which is 1, minus t times the derivative of the bottom, which is 2t. That simplifies to 5 minus t squared over t squared plus 5 quantity squared. And notice that this bottom part is always positive. That will come into play later. When will this be 0? This is 0 for, well, fraction can only be 0 if the top is 0. When t is equal to the square root of 5, or t is minus the square root of 5. But remember, t has to be greater than or equal to 0 in this problem, so that this is eliminated as not in the domain. So there's only one place where the velocity is 0, and that's square root of 5. And we'll approximate that in a bit. Secondly, I need the acceleration, which is the first derivative of the velocity. So I'll take the derivative of this using the quotient rule. And it's a little bit longer, but we can do this. The bottom will be t squared plus 5 quantity squared to the square power, so it's going to be 4th power. Then we start off the top, t squared plus 5 squared times the derivative of the top, minus 2t minus this 5 minus t squared times the derivative of the bottom, which is 2 t squared plus 5 times 2t. And you notice there's a factor of t squared plus 5 and another one here, so we'll use that to change this to t squared plus 5 to the 3rd power. I'm not going to do the algebra here. I'll let you do that. This will simplify down to 2t times t squared minus 15 all over t squared plus 5 cubed. And again, this denominator is always positive no matter what t is, just like the previous one was, and that will come into play. Finally, let's find out when this acceleration is 0. It's 0 for when the top is 0. That's when t is equal to 0 in this first factor, or when t is equal to the square root of 15 or minus the square root of 15. And again, minus square root of 15 is not in the domain, so we can discard that. So we have the velocity function and the acceleration function. The second question was, when is the particle stopped? Well, it's stopped when the velocity is equal to 0. Now, the velocity is 0 for t equals square root of 5, so we have our answer. It's stopped when velocity is t equals 0, meaning when t is equal to the square root of 5, which is approximately 2.2 seconds. So we've answered parts A and B. We want to go for part C, where we were going to talk about speeding up and slowing down. So I need to compare the velocity and the acceleration over various intervals, and for that I will need my usual chart. So let me repeat here that v of t is equal to 5 minus t squared, and on the bottom I'm just going to abbreviate the word positive, and then acceleration is 2t times t squared minus 15 all over, and again this is positive on the bottom, so I'll just put positive there. Then our t-axis starts at 0, and of course again to the left there's nothing. This function does not exist to the left of 0. The numbers we found that were of interest would be square root of 5 and square root of 15. Square root of 5 is approximately 2.2, and square root of 15 is approximately 3.9. Now the initial velocity, the velocity here, it changes when t is equal to square root of 5, and that's the only change. So that'll give me my velocity strip here. The acceleration is only going to change because 0 is one endpoint. It'll only change at the square root of 15. So that's this part. And then the speeding up and slowing down will involve all the divisions because it compares the velocity and the acceleration. Between 0 and square root of 5, pick a number like 1. Putting 1 in here gives me a negative. Well, gives me a 1, gives me a positive rather, positive over positive. So the velocity is positive. Here, for numbers bigger, this is definitely going to be negative, so the velocity is negative. That means we have a stopping point here, which we noted on the previous page, right at square root of 5 time. There's a stopping place for this particle. The acceleration between 0 and square root of 15, if we pick a number like 1, put it in here, we get a negative. And this will be a 1 here, so it's negative. So the acceleration is negative here. For large numbers, this of course will be positive, so the acceleration is positive. Then looking at the comparison between velocity and acceleration, we see that they are different in this first interval. So this is a place where we have a slowdown. In this interval, they're both less than 0. That means they have the same plus or minus signs, so that means we have a speed up. And then here they have different signs, so it is another slowdown. Putting this all together in a picture, we can get one of those nice position pictures. And then once we have the position picture, we can answer the final question about the total distance traveled. So in the position picture, we're going to need to know the position of the object at the 0 time when it starts, at square root of 5, which was of interest, at square root of 15, which was of interest, and then at 5, which was the arbitrary point where we stopped in this part of the problem. So at 0, the initial function is 0, the position function. Square root of 5, it is actually square root of 5 over 10, which turns out to be approximately 0.22. At 15, at square root of 15, it's the square root of 15 over 20, and that's approximately 0.19. And finally, at 5, it's 1/6, which is approximately 0.17. Now we can draw our position graph. Here is the position axis. Here is 0. And this time, unlike the examples we've seen before, the actual position started at 0. So at t equals 0 seconds, the position was starting at 0. Then for a long period of time it goes to the right and then it turns. When did it turn? It turned when t was equal to square root of 5, which is approximately 2.2 seconds. And at that point, from here we get that it had traveled 0.22 meters or feet, depending on whatever the notation was. Then going backwards, it sped up for a while, did not change direction, and then it slowed down, and then here it stopped at t equal 5. And the change between speed up and slow down occurred at t equal the square root of 15, which is about 3.9 seconds. And then at t equal 5 seconds is where we stopped. So we had here, first of all, a slowdown, which makes sense when you think about it. You're moving to the right and you have to slow down before you can stop. Then the first thing you do is speed up. So you speed up and then you slow down. before, once again, you stop here. Or I guess we don't really stop, we continue onward, but we'll slow down until we reach the 5-second mark. And let's see, the square root of 15 gave us a distance of about 0.19, and finally at 5 seconds we were about 0.17. And this distance, as I recall, was in feet, not meters. Now, that still is just a graph. It doesn't answer our question. Our question was, what is the total distance traveled by this particle? And we had not tried to answer that before. Well, this picture is what gives us the answer. Notice that it goes from 0 to 0.22 feet in the first part, and then it travels backwards this distance, which is the difference between 0.22 and 0.17. So it goes a total of 0.22 plus the difference 0.22 minus 0.17, which turns out to be 0.27 feet. So that is the total distance from the point of view of the particle that it has traveled. It's gone this direction to here and then backwards. Notice this is not the net distance. The net distance would be from 0 to 0.17. It would be 0.17. In the end, the particle is only 0.17 away from its initial position. But the total distance it traveled to get there was 0.27. And that's the answer we were looking for here. I hope this is what you got and that you enjoyed the problem.